Hello and Assalamu alaikum everyone. So in the previous sessions, as you saw that we have been dealing with what we call as diagonalization. So in which we had a matrix A, so we decomposed in this S, lambda, S inverse. So that was what we sort of covered in the previous session. So today the main topic of the day is SVD. So it is expanded as singular value decomposition. This is what I will call as grand finale of algebra, because this uses the most concepts that we have studied so far. So it uses concept of rank, it uses concept of null space, eigenvalues, eigenvectors, transpose, inverse, symmetric matrices, orthogonal matrices, positive definite matrices. So the concepts that it uses, I'll just write them down so that you also know. These are the concepts that you must know in order to understand this. So we saw row space, null space, and even the four subspaces that we saw. Then eigenvalues, eigenvalues and vectors. Then we saw different types of matrices, like we saw inverse of a matrix, we saw transpose of a matrix, and then symmetric matrices. Then we saw positive semi-definite and positive definite matrices, orthogonal matrices. We saw all of these concepts. So these are the things will be used in SVD. Okay, so before going to the SVD, let me tell you some applications of SVD. So why is this singular value decomposition used? The first thing, it's used in principal component analysis that we are going to cover today. So this is where it is used, principal component analysis. And the second thing I would like to show is image compression. So when you send image on a network, that time you want to send image in such a way so that the images are compressed. Probably that might be using SVD algorithm. So if you see in Google, Google uses on this page ranking algorithm, page ranking. So when you search something on Google, so it ranks the pages. So it uses this SVD underneath the hood. And even you might have seen Facebook where you see multiple pictures and people get tagged there. So for example, if in a photo there are 5, 6 people, so they tag the faces. So let's suppose this is a picture like this. So they'll tag the faces like this. So this face tagging is done by SVD. Okay, so then there are other applications. I just want you to know these applications, and when we'll be coding this SVD, and we'll probably look at most of them, and then we'll be giving the assignments so that you can yourself cover all these applications. Then something that's called something as low rank approximation. It's also used in that. Then we have other applications as separable models. In machine learning, this also used. The optimal rotation is something we have. There are a lot of applications of the SVD. That's why I wanted to cover this SVD so that you are at least in a position to see all of these applications and then write the real world code for this. Okay, so now I would like to see this SVD, what it basically is. So if you see in the previous sessions, we have been decomposed the matrices. If we had a matrix A, so we decomposed in S, lambda, S inverse. So these we said these are the eigenvectors. But you know that always this A cannot be a matrix in which we have these n by n, uh, in which we have n of these eigenvectors are independent to each other, and this matrix is always a, let's suppose, a square matrix. We can have rectangular matrices as well. So for that we should have a decomposition so that this also can be represented somewhat like this. Okay, so that's where this SVD decomposition comes in. So SVD, it's a decomposition because everything does not need to be invertible. We cannot have eigenvectors, eigenvalues in everything. But the thing is, can we have a matrix? Let's suppose we have a general matrix A m cross n. Okay, can we decompose in something, let's suppose something, then something and something, can we decompose in such a way, and that decomposition is also interpretable. Okay, and it carries a meaning as well. So that's where this SD comes in. Before going into this, let me just give you again that picture that we drew continuously. So we had this picture in which we had four subspaces drawn. So if you see that, so what was so special about these things? So we said, let's suppose we have a vector v over here. Okay, we have a vector v over here. So if you try to sort of apply a matrix A onto this, so we'll call this as a row space, and let's suppose this is column space, column space. Okay, so what I told you that is that if there is a matrix for which we have these eigenvalues, eigenvectors, and it is a, let's suppose, square matrix. We have this A is equal to AV is equal to some lambda V. Okay, so this was our general notion for which we had a matrix A, and when we take a vector, and these vectors were special vectors, these vectors V vectors were so special vectors. So but what I said is that now if you take this is a square matrix. If you now take a rectangular matrix, if you take the rectangular matrix, let's suppose, which is, for example, we have this m cross n matrix, and here we have some n cross 1 vector. Okay, and now you know that this vector will be transformed into some other space. So initially we had a vector that was in Rn. So if you see now the output vector of this transformation, this A, so it will take this Rn vector into Rm vector. Okay, so in this, if you see over here, if you see over here, so here what you saw is that we had these values V, and the V was also output. So they were basically lying in the same space. So again, I don't want to miss out this picture. I'll erase this thing. So when you had this A V is equal lambda V. So what I said is that this A matrix takes this vector V. It scales up, but it still lies in the same space. It still lies in the same dimension, if you see it that way. But if you have a matrix like this, which is sort of a rectangular matrix, okay, so in that, if you take a vector Rn, if you take this vector which is in Rn, so it will be transformed to some other vector space. It's like saying this, I have a vector 1 2, so you know that this lies in R2. So then I will have a vector, let's suppose 1 2 0. So this vector lies in a three-dimensional space, this lies in two-dimensional space. Probably if you see, components are equal, components were equal, but this does not have the z component, this does not have the other component, this does not have the third component. So even if you see that, if you ask this vector a question, you ask him what is your z component, he'll say 0. So if you ask this vector question, what is your z component, he'll be saying, what is z component? I don't know what z component is, because he only has two components. So he is unaware of the fact that there is some component which exists in third dimension as well. So it's like saying, let's suppose I ask a question to a person who is on the earth, and I ask him question about the Mars. He doesn't know about the Mars, let's suppose. So that's the question over here. So here, if you see some transformations in this particular, in this eigenvectors that we saw that the transformation, the vector V was taken to the same vector V with some scaling factor of lambda, and that's what this A did. Now what I'm saying is, if we have a generic matrix of this rectangular matrix, so here the transformation can be like Rn to Rm, where n can be greater than m, n can be less than m, and this can also be equal. So in this equal case, if you see in this case, in the third case, so that we saw, for example, in this transformation of a vector into its eigenvectors and stuff. So here we dealt with that case. But what if we had a matrix that's wide, in which number of this n is greater than m, we have a lot of columns. So if you now take a matrix, let's say we'll take a vector which is of or n, so now it will be taken to Rm. So in the other case, if we have a taller matrix, so that is we have m cross n, and m is greater than n, and then you take again this Rn, so this will be taken to Rm. Now the thing is, here you see that this m is less than, this m is greater than n, and here m is less than n. So now we'll see this decomposition where it works now. So now this is clear, I think. So now if I take a matrix A over here, so take this A, this let's suppose is a rectangular matrix. It is not the matrix like this, not a square matrix. Okay. Now this A, what it does, it takes this V1 to it takes to this V1 to some other, let's suppose U1 in here, U1. Okay, that's the picture I want you to see, because most of the times you don't lie in the same thing, you don't lie in for example the same vector space. This you can just take the vector, you can transform into some other vector space, as happened in this. We took this vector from this and we shifted it to some column space. Okay, why column space? Because I know that this vector, this, it belongs to, it has dimension r, so here vectors will belong to dimension r. So you know that this is of dimension n minus r, if you see that. So here we have this column spaces of n minus. This is basically that m minus. You have to look for the dimensions exactly. This is r is a rank. So here you look for that also. So that's what I'm saying. The vectors will be taken from this v1 and they'll be shifted to this u1. So I can write it like this. So in a general transformation, if I take a vector, if I take a, and if I take this u1, it will be taken to some v1. Okay. So this u1 was in here, it was in the row space initially. Now we changed it to the column space. And you know those small pictures that we had, like there we had. So I'll just erase this so as to keep this picture neat and clean. So here we had this null space in the both cases, and I don't want to do those. So this is what we had that time when we drew it. Okay. So these are null spaces, null space of A and null space of A transpose. So, but what I'm interested in is that I am taking this V1 vector and I am shifting it to I'm getting it onto this U1, and this is how I do it. This A U1 is equal to some V1. But what I'm doing is I want this vector to be unit vector. Let's suppose I'll take this unit U1 to unit vector. So I can just write some sigma 1 over here, and I'll say, oh, this is actually V1. I just need to, this is A V1 and it is taken to sigma U1. So here this is some scaling factor and scaling factor, and this is unit vector. That's what I did. I only did one thing. I had some vector, let's suppose u1 dash, which was not unit vector. In order to convert it into unit vector, so I made a unit vector u1. So now I know that actual vector which we took this v1 to was u1 dash, but now I just multiply it by that sigma 1. I multiplied by sigma 1 to get this. So now the expression that you have is a v1 sigma 1 u1. So this is this transformation. If you have a matrix A, okay, it takes this vector v1 into this u1. That's the notion we have. Now you know that there will be bases onto this. So there will be bases. So there will be bases of the vector which will span whole of this. Okay. So how many vectors will be in the basis? So here we have, this is of dimension r, so there will be r bases. Okay. Similarly, we can take we can go into this. So how many will be there? It depends on the that m. So if here it was n, so here it will be rm. So vector belongs here into rm. So that m it belongs to. So what I want to tell you that here the bases I want are orthonormal bases. Orthonormal bases. I want those bases and I want to transform them somehow into this, and I'll get bases over here also. I'll get basis vectors. They should also be orthonormal, let's suppose. Okay. So I want to convert this v1 into some u1, and then I want to convert that v2 into some v2. Okay, into v2 to some u2. But the property they should follow is that all the things are v1, v2, v3, they should be orthogonal to each other. Okay, then I'll normalize these things. That's the whole picture I want you to visualize. So again, reiterating this, we have a vector v1 over here, and we have this transformation A. This A transformation takes this v1 to u1 with some scaling factor of sigma u1, because I want this to be unit vector. So that's the picture I want you to see. Is it clear?
Yes, sir.
Because you know that a vector in here, a vector in this row space lies in Rn, and a vector in here lies in Rm. That is, you know that. When we were dealing with this column space and row space, that time you know that the vector, the output vector that will be in the row space, it will be Rn, and the output vector of this will be Rm. These vectors will lie in this Rm. So that's what I'm saying here. So you have to take these vectors v1, v2. There will be a lot of vectors over here which will be orthogonal to each other, and you will take them over here. Okay. Now we'll see the procedure how to take them over here. So now if you see that, we'll have this AV1 is equal to sigma 1 u1. Similarly, if we take a vector which is orthogonal to v1, that is, let's suppose v2, we'll take to sigma 2 v2, something like this. And again, a, let's suppose vr, there will be r vectors. So that we have sigma 2 sigma n, let's suppose this is n vector, not r just. So this will be a vn, so this will be sigma un. This is the picture that we have. Okay, you know that we can collect these vectors now and just write them in a succinct version, so that we'll see what's the whole point of these singular value decomposition. And these vectors, these values are called as singular vectors. These vectors, these. So if you see that, we call something as eigenvalues. So here we had that a is equal to av is equal to lambda v. So we call this lambda as eigenvalue. So here if you see, we have some other notion. We have a notion of a, some v takes it to some sigma u. Okay, so here in this expression, these are called as singular values. Singular values. Okay, and these will be obviously called as singular vectors. Then we call them, say, this is called as right singular vector, right singular vector. And this is called as left singular vector. Singular vector. Is it clear? So you saw the parallel that I'm drawing by this eigenvalues and eigenvectors, and I'm parallelly doing something, because it won't be always the case that we'll have that v and which will lie in the same way. V will be transformed to some view. Okay, but the special thing is that it will be again the unit vector, and we have the scaling factor of sigma. So are you seeing the analogy between this? So are you able to see that analogy between the eigenvalues, eigenvectors, and the singular values and singular vectors? Are you able to see that?
Yes, sir.
Now how I will collect
Yes.
that is, I can write a Okay, that's my A. And then I'll have this V1, V2 till VR, because you know dimensions of this column space of this is basically R. So I can collect these R vectors, okay, and this will be, and then I have some other vectors, maybe some vectors which are from null space, and this is AV basically. That basically should be equal to our other vectors that we take in the U. Okay, so there we have the singular value. So we'll have sigma of, let's suppose, sigma 1 U1, that will be one column, sigma 2 U2. I'm just writing this thing. I'm just clubbing whole of this and making it in the matrix notation. So this is A, and then I'm taking this V, that's equal to sigma 1 U1 till, and so on. So I'll write this like this. So what I can do is I'll just separate out these sigmas. So this side I'll separate it out. I can write it like this. If you have seen the previous lecture, we did the same thing over there. So U1 will be over here, U2 will be over here, and so on. And then we'll have this sigma 1, sigma 2. Okay, and this we have this A and this. So now if you see this vector, we'll name these now. So this is now sigma, and this is our U1 to let's suppose this is UR. Okay, and this is our sigma R, and we have some other things. So now we'll name this. So this I'll call it V. Okay, this I'll call it V. This I'll call it V, and this I'll call it U. And here I'll call this a sigma, bigger sigma. So what I can write it is that A V is equal U sigma. This is what I can write. So if I apply inverse on both sides, so what I'll get is I'll get A. Okay, I want to apply V inverse onto the both sides. So I'll apply V, and V inverse is equal to U sigma V inverse. So this is what I'll get so far. So what I'll do is, so I'll write A is equal to U sigma V transpose. Why I can do that? Because you know that this is an orthonormal matrix. Because that's the assumption we had. These bases we are taking that orthogonal. So you know that V transpose V is equal to I if we have orthogonal matrices. Okay, that's what I'm writing here. This here is SVD. So here we call this as matrices which contains these left singular values, left singular values, and here this contains right singular values. Okay, and here this is the matrix of singular values, vectors. I think here it is vectors. Again, just going through it again. So what I told you is that there is an analogy. So if you have a matrix which is square matrix, and square matrix usually we can decompose them into the eigenvalues and eigenvectors. So I told you that this is lambda, and we have V, and we'll have lambda V1. So if you want to decompose this, you saw that if you remember the notion of that diagonalization, we said we had this A, and then we had this S matrix, lambda S inverse. So these S matrices over here, they have a bunch of eigenvectors and eigenvalues. Then what I said is that every time we won't have this matrix in such good format. So let's suppose we have a matrix like this in which we have this m cross n. If you take any vector Rn, it will shift it to Rm. So basically the vectors don't lie in the same space now. So in order to see that, what I said is you can do one thing. You can respect only one thing, is that you take this v1 vector and convert it into some u1 vector, and all the things should be orthogonal to each other. So if you take v1, v2, vn, they should be orthogonal to each other, and similarly in this u1 column space, they should be orthogonal to each other. So from that I got this av1 is equal, I got this av1 is equal sigma 1 u1. Okay, then in a similar fashion we'll have this av2 sigma 2 v2 till this n. Okay, and then what I told, I collect all of these v's into a matrix. So I said A, and then collect these v1 v2 till vr, and similarly I'll do the similar thing with on the right hand side, and this equation boiled down to av is equal to u sigma. I applied the inverse on both sides, so I get this A is equal to u sigma vt. So if you again see that, if you again see our A is equal to s lambda s inverse, if you see this, okay, you know, in terms of if this is orthogonal, so if this S is, let's suppose, orthonormal matrix, so you can write this as A is equal to S lambda ST also. So you can write it in the you can write it in this fashion, and that time you know that this V and T will be equal. So but this is only in the case if this A matrix, this matrix is a good matrix, and that we were seeing. But in order to have a general matrix, so this notion won't work for all the matrices, that diagonalization, because I told you some matrices are not diagonalizable. But this works for everything. If you have any matrix, and you can decompose this matrix into this U, which we call as left singular value matrix, vector matrix, and then we have this VT, which we call as right singular value matrix, and these summations are singular values. Similarly, as we had these lambdas, which were eigenvectors, eigenvalues, and then we had corresponding eigenvectors to that. This is what I mean by singular value decomposition. Now the question remains that how to find this U and V, how to find this U and VT. Okay. So initially we know that how to basically find if you have these eigenvectors, eigenvalues, and we have the formulation for that. Now the question here is that how will we find these things? How will we find these vectors which will go to U? How will we find these vectors which will go to V? For that, we we need some other tools, and that we have studied so far, and we'll see them and how to use them. And I just wanted to add one more thing. Why are we decomposing it in this way? Again, I told you that intuition behind that is, let's suppose we have this A which is equal to some BC. I said that if there is a vector space, if you perform this C transform first, then B transform first. So that's equivalent if you just perform this A transformation. Similarly, if you have this matrix A, okay, and then you have this U summation VT. So what it does is, if you know this is a matrix of orthonormal, and you will call it a rotation because it will rotate it. If you know the properties of these orthogonal matrices, so they basically rotate the space only. So they rotate in certain direction. So if you again go back to those visualization which we said. So if you have a matrix which is orthogonal, so it will rotate. So here it is a rotation matrix. So it will rotate, and this will basically stretch it in certain directions. Because if you see the diagonal matrices they stretch the things. So diagonal matrix, they stretch the things, and there are the other thing that is rotation matrix, they'll rotate our whole vector space. Again, this is again a rotation. This is stretching, let's suppose, or maybe we could stretching. Stretching is a good word. So what I can say I am telling you that if you give me any transformation, in the world, so what I can do is I can convert that into three rotations. I can convert that into three sort of transformations. The one is rotation, then apply some stretching, then apply these rotations. If you have seen, for example, any sort of game, so there are a lot of rotations that will have to happen. For example, if you have to move the scene, if you have to switch the scene, so there will be complex rotations involved. But what I told you is that any rotation can be decomposed into this. So if you see it in the graphics world, so any rotation can be any sort of transformation can be decomposed into a rotation, stretching, and rotation, if you got the intuition right. So what I'm telling you is that this A is some transformation. It does something to the space. So, but that might be really complex to look at. But you can decompose this into simple things like rotation, stretching, and rotation, and you'll be able to visualize this. Is the visualization part clear?
Yes, sir.
We'll take concrete examples to let you visualize these things. But here, what I'm telling you is that there is a possibility that any complex transformation, you can just decompose it and convert into these rotations and stretching. Okay, now let me tell you how to compute these vectors in U and how to compute these vectors VT, and what is so special about these things. Until now we have been doing this SVD, and now we have the expression of SVD. Now we need to compute this U and VT and vectors in there. Okay, so how to do that? So there is a really good thing that you have studied. You saw that if we have a matrix A and A transpose, okay, and we had other matrix ATA. So these were our two matrix. If we had some matrix and we just performed these operations, and the thing in there was these matrix has special properties. So what are the special properties? If I remember, the first special property about these was that these matrices are symmetric. So they are symmetric, and I think we proved these properties. So this AA transpose is symmetric. This A transpose is also symmetric. So I said you that A is M cross N. Okay, so if you see this A transpose, so what will it will be a symmetric matrix. So it will give us some value. Let's suppose we'll have some matrix. But what is the dimension of that matrix? So if this is M cross N, so this will be N cross M. So this will be M cross M. This matrix. Okay. Similarly with this, so we'll have N cross N matrix. The best thing about these things is that these are symmetric. That's the first thing, symmetric matrices. What is the property that we saw about the symmetric matrices? We saw that these matrices have orthogonal eigenvalues. They have orthogonal eigenvalues. If you remember in the previous lecture, if we have a symmetric matrix, that matrix has the orthogonal eigenvalues. And you saw that the eigenvalues are also real. So these matrices are not just orthogonal, they are also positive definite matrices, at least positive semi-definite. That means that eigenvalues, orthogonal eigenvectors. So eigenvalues are positive. That lambdas are greater than 0 if you see it over here. So these are nice properties. Okay, so what I'm telling you is that A transpose, they are symmetric, their eigenvectors are orthogonal, and they are positive definite, and due to which lambda is greater than 0. These are the good matrices that we wanted. Now how can we use that? So if you see this, now taking this example, taking this A80A, okay, so ATA can be decomposed because it's a symmetric matrix. Okay, it can be decomposed into this V lambda V transpose, our old diagonalization, or we call it spectral theorem. Sometimes you might see it in the book, written in the books, spectral theorem. So I can decompose it like this. So here these will be eigenvectors. So eigenvectors of what? Eigenvectors of A transpose A. So this I can write it in this format. Okay. Similarly, I can write this A transpose into some U lambda U transpose. Because it's a symmetric matrix, I can write it like this, and this symmetric matrix obviously is square matrix, so I can like it like this. So here these are eigen vectors of A transpose A. Is it clear so far? Because I have to derive these things from these things. Is it clear?
Yes, sir.
Yes.
Okay. Now I'll go forward and see how I can derive, how I can get this U and V transpose of this A. Okay. So what I will do is I'll write A is equal to U sigma, and the other thing was V transpose. Okay. So if I write A transpose, so that means A transpose. So what I can do is I can write this A as it is, U sigma V transpose. Okay. Then A transpose means reverse everything over there. So when you reverse it, it will become V. So this will become sigma transpose. This will become U transpose because I'm transposing this whole thing. So you know that A, B, C whole transpose is basically equal to C transpose, B transpose, A transpose. That's the property that I'm using here. And I'm taking whole of this transpose, that boils down to V. This is sigma transpose, this is U transpose. That's what I wrote over here. But you know that this V vector, these vectors are orthogonal. The vectors that are in those matrices are orthogonal. So this becomes I. So if you see, this becomes I. So this is equal to U sigma transpose UT. Okay. Now you know that these things are diagonal matrices. So it's like this. For example, we have 1, 2, 3, and then we have something like this. Uh, you have the diagonal matrices are symmetric. So you have like this. So this is just square of this. So this is equal to U sigma square UT. Okay. So this is how you can compute these U values. So these U values can be computed by using this AA transpose. That's what I showed you here. That's why I wrote in the initially, if you saw in this AA transpose, what I wrote U lambda U transpose. And now if you see this lambda basically, or these eigenvalues, basically here we have this sigma square. So we have to apply the square root on these things and onto this thing. So again, this A, just remember it, A is equal, why am I writing it again so that you memorize it. So U sigma and then V transpose. So now I'll do A transpose A. So A transpose is again, I'll write it V sigma transpose U transpose, then A is, this is A transpose, then here I'll write A. So A is equal to U sigma V transpose. So now if you see this again becomes identity, because you know that the vectors that are in U, they're orthogonal to each other. So the property of orthogonal matrices are U transpose U is equal to identity. So this basically boils down to V sigma transpose sigma Vt. So say same again, V sigma square Vt. So that's why using this matrix you can compute these V's. Are you able to see this picture? How to compute these things now? So what I said, if
Yes.
you want to compute U's, so which matrix you have to use? You have to use A transpose. If you have to compute these V's, you use A transpose A. Okay, this is what you have to do. I think it's a good time to do an example. So as to show you these things, let's suppose we have a matrix A. For matrix A, this matrix is, let's suppose here I have an example written 4, 3. This is, let's suppose, minus. Okay, so you know that this v1 comma v2, whatever we'll have, v1 and v2, they must be in row space of this, and the row spaces are 2. Okay, because both of these vectors are independent. Again, the similar thing, u1 and u2, they will be in the column space. They'll be in column space. The column space is also in R2. Okay. So now this is a positive semi-definite matrix. So what we'll get when we'll have those things? So we'll get these sigmas. Sigmas will be greater than 0 that time, because if you see this A transpose, so they are positive definite matrices, so the lambdas will be 0. Lambdas will be greater than 0 obviously when you take square root or square of these numbers, so they'll be greater than 0. They are positive definite matrices. Okay, so now let's do one thing. Let's first compute this A transpose. Let's compute this first. Help me in the computation. Keep your pens and papers ready, because I have a tendency to make these computations wrong, so let's do it together. So A transpose is, again, this is 4 minus 3 4 3. It's a transpose. Now let's do this. So this multiplied by this is 16, 16, and then 16. This is 32. Okay. So now this is 12 minus 12, and this is, I think, 0. Is it? Just check it once. So this
Yes, sir.
is 0. Obviously, I think here it will be 0 because it's symmetric matrices. Now we'll be doing it 3, 12. So this is 9 and plus 9. Is it 18? Just tell me this. Is it 18? I have written the computation somewhere, but I cannot find it on the right time though,
Yes,
whenever
sir.
I need to perform computations. Okay, I think if this is okay, so we can move ahead. So this is our A transpose. So the thing is, we need to compute its eigenvalues and eigenvectors. Now you can, I think, obviously see these things. So this is our A transpose. So the eigenvectors. So what will be the eigen? So obviously there will be two eigenvectors and two eigen values. So here, tell me the eigenvector. How to compute the eigenvector? So eigenvectors basically means if I multiply by something, so that should remain that something only. So what are the eigenvalues and eigenvectors? Can you just compute them? I'll just wait here for a few seconds so that let you compute these things. I'll just pause the record. So the eigenvectors and eigenvalues, I think here we have 3210 if you take this, and if you take 1601. So these over here and these over here are my eigenvalues, and these over here are eigenvectors. Why it's really easy to compute. So take this 10. So take 1 over here, 10. So if you just multiply 10, so it will remain 10, but it will get multiplied with this 32. If you take 10 over here, so it means take one of this and none of this. Okay, so it will be 32 0, and take 32 out of this, so it becomes 10 again. So but eigenvalue is 32. Similarly, take 0 of this and 1 of this, but take 18 out of this. This should be 18, sorry, not 16, 18. 18 out of this, so these are eigenvalues. So is it clear, the eigenvalues and eigenvectors for this? Is it clear?
Yes,
Now,
sir.
now just keep this in your hand, and now we have this A transpose A. Again, doing that computation. So this is A transpose and multiplied by A. So this is 4 4 minus 3. So here we have this 4 minus 3 and 4 3. This is what we have. And if you compute this thing, so this should be equal to, can you compute? Give me the values. So this will be 4 16 and then plus 9. 16 plus 9 is 16 plus 9 is
25.
okay.
25.
So that you just respond to me, because the thing is, I can make mistakes and you will have to correct these mistakes of me. So now you have to compute this A transpose A matrix. Give me the values directly now. So I again pause the recording. Give me the values. This is just an exercise for you guys. So this is our A transpose A. So this is this A, and this is our A transpose. This is our A. So when we multiply them, you get a symmetric matrix like this. Now you have to find its eigenvalues and eigenvectors. Can you do that? Can you do the computation faster? Take one of this in order to find the eigenvalues and eigenvectors. Take one of this and one of this. So if you add these things up, so this will become 7 plus 25 plus 7 is 32. 7 plus 30, this is 32. So if you take the vector, so you will get, by taking 1 1, you will get the output as 32 32. So you can take this out, this 32, and you can write 1 1 over here. Okay, so this is the first eigenvector, and this is its corresponding eigenvalue. And similarly, we can take one of this and minus one of this. So this again will become 1 1, and the eigenvalues will be, I think, 25 minus 7. How much is this? it is 18. These are the eigenvectors, and these things are eigenvectors. Eigenvectors. So these are our eigenvalues. Okay. Now see the interesting thing. So we had this A transpose and A transpose A. So you see that eigenvalues remained as it is. Eigenvalues are same. See, so it is not just happening in this example. So it basically is a fact. So the eigenvalues of both of these are basically same. So again, see this. So here the eigenvalue 32 and 18. Similar thing happened here, 32 and 18. Eigenvectors are different though. So similarly, so you can establish from these, the matrices are so special, so that if you take the eigenvalues, they are similar, but eigenvectors are different. The scaling factor is same. Okay, the eigenvalues are same and eigenvectors may be different. Now what I said to you is that if you have this matrix A, bigger matrix A, so you wrote U summation and then V transpose. That's what you have to do. Okay, so you have to collect these U's and you have to collect these V's and write in the sigma. Now we have everything. If you see, we have everything. This is our U1. I think these are U1s, because we get from A transpose we get U's. So from A transpose A we get V's, and from A transpose A we get U's. So the first thing is A transpose you get U's. So this is our U1. So this is our U1 and this is our U2. Okay, and similarly the second thing we have here is A transpose. This A transpose A. So this is our V1. This is our V2. V1 and V2. Okay, now you have to normalize them. So normalize means, because we are assuming that these vectors are orthonormal to each other. In order to normalize, how will you normalize? So if you have, let's suppose, a vector 1 1 and you want a unit vector out of it, so how to get unit vector? You just normalize it. You'll say 1 1 and under root of 1 plus 1, under root of 1 plus this 1. So this will be by root 2 by root 2. Okay, similarly if you have this 1 minus 1, the similar thing over there, so this will become 1 by root 2, 1 by root 2 but negative. And then we have these vectors. If you see these vectors, 0 1 and 1 0. So 0 1, this is normalized, so 1 0 is normalized. Okay, now you know that you have to put under root over there. So if you see these equations, so you have to just put under root of 32 under root of 18. So because you got the squares over there, if you see these numbers, so this V sigma square Vt. So in order to get that lambda, so that basically will become the under root of things, and just putting the everything together, so you can put, now we have these things, we have this, we have this, we have this and this, our U1s, U2 and V1 and V2. So we'll just collect them into a matrix and you will see them. So this is our let's say V1, this is our V2. Similarly, this is our U1, this is our, let's suppose, U1 and U2, because these are the transpose. And then these summation matrices, there we have the diagonal matrix, root of 32 and root of 18. Now you can put everything together. You can make this matrix A as, write this matrix U, here you will write U1 and you will write U2, then you will write the sigma. So here it will have the value sigma 1 is root 32, this is like sigma 1, this is sigma 2, and similarly you write V1 transpose is like this and V2 transpose is like this, and this should be equal to this. Is this example clear? But this was the case where we have this was a case where we had a matrix A in which that was invertible, because both of these columns, if you see this, this and this, so this was our matrix, both of these columns were independent to each other. But what if there is a dependency? So what if there is there are dependent columns? So that time you know that these vectors, these won't be full, that basically won't be a full rank matrix. So full rank matrix, because of that thing, we won't have this U1 U2 and stuff like that. We'll have just U1 and the other vector will be the vector from the null space. So okay, let me do an example like that also. So all these examples are taken from the book by Gilbert Strang, Linear Algebra and Applications, so that my calculations becomes easy. So let me take another example. So this example is the example in which I want a matrix which is basically low rank matrix. Low rank means that there are some columns which are independent. I'll just do it with true clause 2 because otherwise it will take a lot of time. The example that I have is 4 8 3 6. So both of these columns are dependent on each other if you see it. So it's a rank 1 matrix. This is just rank 1 matrix. So if you see, if I make a picture of column space, so if I make picture of column space and row space, so how will they look? So if I make the picture of column space first, so column space, basically you take this 4 8, so there'll be a vector like this. So let's suppose this is 4 8, and every vector will lie in this column because it'll be a line. Why will it be a line? Because every vector, for example, this 3 8 can be represented in this 4 8. So how you can write this? So you can write 3 6, and then have you can write this 4 8, because you want to represent 3 6 in this 4 8. So 3 6 can be written like this: 3 by multiply by 3 by 4. You see this, you will get this 3 by 6 now. You'll get 3 by 3 6, not 3 by 6. So this will be cancelled and you will get this 3. So here this is 3 multiplied by 8 by 4, 4 ones 2, 3 6. So this is the scaling factor. That's what I'm saying. These two vectors are both inverted. So it means the column space lies on this line. So again, if you see this null space, it will be like this. That's the column space. The column space basically this is 4 comma 8 scaled vector, 4 comma 8. Okay. Similarly, if you see for this row space, so row space is this 4 3 and 8 6, and you have to find can we get this 4 6. I think we can. You can also get it. So column space and row space. So row space will be basically 4 3. So let's suppose 4 3 is something like this. So this will be our row space, and this will be our null space of that. So this is how the picture will look like. So if you see it, this and this picture for this matrix, this is our null space of, if this is row space, then it becomes null space of A transpose, and this becomes null space of A. That's what we have seen so far. Okay, and if you want to normalize these vectors, you can get the normal value of these vectors as well. So because this 4 8 is basically the basis, and you want to normalize it, and again this 4 3, this is the basis. So here I'll write that 4 3, this vector, this is line 4 3, this line. So these two are the vectors which are basis for the column space and the row space, and similarly for the null space you can get it accordingly. So is it clear so far? So here you saw that this whole column space is represented by 4 8. So here you saw that this whole row space is represented by 4 3. Okay, so now we have this transformation A which takes this to this. Okay, now you have to get one thing, you have to normalize these vectors. The normalization of this, that is easy, like 8 square plus 4 square under root, and that you'll get the value. 4 square plus 3 square under root, you will get the values from this. So now what I'm telling you is that this is A, this is our A. Okay, and matrix is 4 8 3 6, this is our A. So then we have this U matrix. So U basically is, if you have this AA transpose, so what will happen is it will take this AA transpose and it will get U out of that. I think AA transpose, if it is right. So we get U's by this AA transpose, right? So AA transpose gives us this U's, and A transpose A gives us this V's. You don't have to memorize them, but you can just derive on the fly. So if you have a vector, if you again remember this picture, if you again remember the picture that we had so far, this picture, the first picture that I drew of SVD. So here we have this row space. Okay, this was our V1 vector, and then it was taken to that U1 in the column space. Again, I made that picture over here. So I made a picture clear for this example. For this particular example, I made the picture. So this is the row, and this vector will be taken to somehow this vector by this matrix A. Okay, but these vectors should be normalized. Okay, so if you normalize this row, and you will get the vectors accordingly. So I'll just write the normalized values. So I'll see the normalized value. So U, it is 1 by root 5 and 2 by root 5. This vector, I mean this U vector. So this is U vector. So how you can write it? This 4 8 can be written. I'll just show it. So 4 can be taken out. So this will be 1, and this will be 2. So 1 2 is the basic vector, because 4 8 you can write 1 2 instead of this, because that lies on the column of this. So if you, in order to normalize this, you can just divide it by 2 square plus 1 square, that is 5 square, that is root 5. So that's why the normalized vector lying on this is 1 by root 5 and 2 by root 5. Is this clear? That's why this I got this U1. I wrote 1 by root 5, 2 by root 5, because the column space was 4 8. That can be basically written as 1 2. This is what lies in the column space. Every vector can be represented in the form of 1 2. So that's how I got this U. Is it clear?
Yes, sir.
Okay, so this is our U. Now you know that this vector won't be there of U, because you know the rank is the lower rank matrix. Now we'll have the sigma, a sigma matrix, and then we'll have V. If you see this U, this is capital U, I used it, and this sigma, this is V transpose. Now what is V over here? So you see this 4 3. So again, if you just take 4 square and 3 square, it becomes, I think, 0.8 and 0.6. So here the normalized vector of this is 0.8 and 0.6. So this is the normalized vector. Okay, if I'm right. So that you can write it like this. So this is the thing. V transpose. So V transpose, you can write it. So maybe I'll write it. So first I'll write the sigma, because sigma here will be, these will be zeros. Everywhere will be zeros. Why? Because it will have only one sigma. Because this is a lower rank matrix. So here it will be some sigma 1, some value will be over here. That will be there. So in order to find that, let me show you this. So in order to find that, we know that A transpose, you use this to find U. This is that A transpose. A transpose is used to find U, because the matrix, it's like this. This is our matrix is 4836 multiplied by 4836. Again, the answer that it gives is 80, and this is 60, this is 60, and this is 45. This is the answer I got. Now I know that 1 lambda will be 0 guaranteed. Why? Because this matrix, if you see this A matrix, it is rank 1 matrix. It's not full rank matrix, because the columns in that are dependent. So one will be obviously 0. The other will be, because you know you have to sum up these diagonal entries, then you have to sum up these. So other things will be 125. So this is lambda 2. Okay. Now in order to get the sigma, you know, you have to take the under root of this. So in order to get this sigma over here, you have to take under root of eigenvalue. So eigenvalue under root will be root of 125 will be this sigma 1. So other sigma will be 0. So this will be root of 125. This is how I got this. Okay, now I want to get this. I'll get this A transpose. This V transpose basically. So I told you that the vector over there that we had is 0.8 and 0.6. You have to transpose it. So you'll get 0.8 over here and 0.6 over here. Okay. So now here the vectors here, whatever vector here, you will get this vector. It will basically, because this over here is Ru, and these vectors will belong to null space. This vector and this vector, they'll belong to null space, because they have to produce this 0. Okay, they have to produce these zeros. These vectors, if you see, this belong to our a column space, a row space rather, and this belong to our column space. So that's what you see. Whatever vector you fill over here, whatever vector you fill here, that should give me these 0 vectors. Okay. So in order to see those, what are the vectors? So I'll have, so I'll just, without computing, I just want to see the answer. So what is the answer? So here it is 0.6 and minus 0.8, because this is the vector which is perpendicular to the 7. So again, this is, let me see, this is negative of, this is 2 by 5, 2 by root 5, and this is negative 1 by root 5. Okay, now you saw that entry. So if you ask me, if in the case of why we have this dependent columns, so you get only these sigmas. Okay, and sometimes it will be other way around also. For example, it can be a matrix, you'll have like this. So what I'm saying is, you'll have A and you'll have some U, and the sigma will be like this. So you'll have sigma 1, sigma 2, sigma up till R, because that's why if we have this R rows in here. So you'll have U1, U2 till UR, and then some vectors from the null space. And you will have these sigma r's, and then you will have zeros filled over here. Okay, then you will have this other vt, which will have u1, u2, and so on. Okay, the other vectors that will be here, I think it is like this, v1 transpose and v2 transpose. Something like other vectors that you will fill will be from the null space. So is the other two examples clear? Again, to just rephrase it, the thing is, in the SVD we have a matrix A, which is decomposed into 3 matrices. The first matrix, we'll call that matrix U, and then we have sigma, then we have V transpose. Okay, so here the sigma matrix is called singular values, so they have singular values, singular value matrix, and this is right singular vector, and this is left singular vector. In order to find this U, we are saying A transpose, we'll be finding U, and then we'll have this sigma square, basically sigma square U transpose, I think, and then we have this A transpose A, which gives us V sigma square V transpose. This is what we get. We are using these two equations. Then there can be two cases. The first case is that if matrix is full rank, let's suppose. Full rank means all the columns are independent. You'll get, and in the second case, if it is a low rank matrix. By low rank, I mean The all columns are not dependent, all the columns are not independent, there is some dependency, low rank matrix. So in the first case you saw that you will get this sigma will be like this, sigma 1 till sigma n. Okay, and but in this case you saw sigma 1 and sigma 2, let's suppose, then it will be followed by zeros. So this covers our SVD. I give you all the examples and all the things to derive, but in practical scenarios, you won't see how, because you'll use this A transpose. It's computationally really heavy. So if you tell me in the real world how do you compute this A transpose and A transpose A to compute this, you will know. So we use some other methods, but that's the basic derivation I want you guys to know. Okay, this is where the singular value decomposition comes from. Is it clear?
Yes, sir.
So let's suppose we have a circle like this. We have a circle. Let's suppose this is our circle. Okay, this is our circle. Let's suppose this is like this. So what I want to do is I want to do A is equal to U sigma V transpose. So when you apply the transform, you will apply this V transpose first, then you will apply the sigma, you will apply this U at the end. So what will happen by this V transpose? It will basically rotate it. It will basically rotate the circle and change its basis. Okay, this circle will be rotated, and the basis got changes. So basis got, let's suppose this was the base and this is the basis. Initially we had, let's suppose, this and some this, so it got rotated like this. These are the bases that we got, because I told you these are rotation matrices. So they'll rotate them. So they'll take this, let me write it with blue, and this is what V transpose does. Okay. Now what will this lambda do? So this sigma basically. So sigma has, let's suppose, lambda 1 and lambda 2. Okay, and the rest will be 0. So it will stretch the matrix. So it will stretch it. It will stretch the this transformation. So what will happen? Let me just write it with different color. Okay, so it will, let's suppose sigma 1 is greater than sigma 2. So let's suppose sigma 1 is this. So it will stretch it like this. It will stretch it like this. Okay, now this is my sigma 1. Let's suppose I'll stretch it a little bigger. Okay, and the first stretch is a little bigger, sigma 1, and this is my sigma 2. Okay, so this is my sigma 1 and this is my sigma 2. This is what this summation did to it. And if you see again this picture, what will this view do? You again know that it will just rotate it somehow. Let's suppose this got rotated into this fashion. This got rotated somehow like this. So again there will be sigma 1 and sigma 2 will be like this. This is some rotation. Okay, so what I did is, this is the total, that this is at the end what we got. This is the end result. Okay, that was done by A. So A was a transformation. I showed you that this transformation can be broken down into rotation, then stretching, and the rotation again. So this is the first thing was rotated like this, and then this rotation was stretched. Okay, and then this was again rotated. So that's how we can show it visually if you see it. Is it clear? So again, the best thing that we have is, so I again like to show you one more thing. So if you see this A, and this is our U, this is my sigma, this is my V transpose. So all the sigmas are here, sigma 1, sigma 2. Okay, so whatever they are arranged in increasing order. Like the sigma 1 is more important than sigma 2 is more important than sigma 3, and so on. Okay, the arrangement basically is ordered in the in importance. That we'll see when we'll code the things, what is the meaning of importance and how do we use it in image comparison. But you must know these things, that this is the order of importance. Okay, so we'll take the bigger sigma 1 first, and then other sigmas followed by that. This will be basically increasing order. This will be in decreasing order, sorry, decreasing order. So first we have bigger, and this is ordered in terms of importance. How much is important? That means that u1 is more important than u2. Again, in the similar fashion till you are. Okay, that's how we can perform the compression, because sometimes you'll just use two of these to show the image. Is it clear? Is it clear?
Yes,
Yes,
sir.
sir.
Zubair, Jahangir, Rian, is it clear? Nice.
Thing.
Hey, what's math
Yes, sir.
telling you is, guys, that when there are two phases to what I teach. The first thing is I want you to have mathematical intuition, mathematical thinking. Why is it happening so? Why is it for example, singular value decomposition, what is the meaning of that intuitively, and how can we mathematically derive? So in the next phase, this is my phase 1. So phase 1. So all of these algorithms I'll teach you again. So this is not the end of these algorithms. So I'll reteach these algorithms. I'll reteach the algorithms. I'll again take SVD. I'll again take PCA. I'll again take linear regression. I'll again take all of these algorithms. But that time I won't tell you the mathematical details. I won't tell you how to derive these things. I won't tell you what is the meaning of this mathematically. There we'll directly apply them on the data. That will directly apply them onto something. For example, we'll take an example image compression, and that time we'll see how SVD is used in image compression. We'll take example of some, let's suppose, stock prices, and we'll see how linear regression can be able to, from that we can able to detect stock prices and things like that. And the phase one is the phase that you are right now into. So you have to learn the mathematical details and mathematical intuitions. Why is the equation the way it is looking, and how to transform it into the real world. And in the second phase, we'll be using all of this, whatever we learned, into real world applications, and which will build after having this mathematics. There you will find most of the videos only focusing on this part. And if you are going to take get the good interview calls there, you'll find a lot of questions being asked from this mathematical part. Okay, why do you think it works this way? Why do you think this should happen, this should not happen? And there will be a lot of questions. Even in the yesterday's interview, I asked some questions related to regression to the people. Okay, what do you think this, why does that happen? And uh, it so that's where in this phase you must know this mathematical details, because in most of your interviews you'll face the questions regarding mathematical details. They won't be asking you what is linear regression. They'll be asking you, okay, what do you understand by regression in terms of mathematics? Okay, what is the meaning of SVD? Why do you even do this? So there you'll have a lot of questions from this and from this. And here we will get to know, okay, are you able to now implement these algorithms? There are two types of people. There are research academicians and there are really good coders. These two people is really hard to get. For example, somebody is really good at theory, but he cannot implement the algorithm because he's very less acquainted with the code and stuff. But I want you guys to be have to have both. At least have some mathematical notion, be really good at this, and be plus good at this, because this is what you will do in your real job. But this is the intuition that will land you at the job. Okay, that's the notion I wanted to give you. If you have this and if you have this, you are on superpower. You have both the charts. You have mathematical sense also, and you know how to code these things. And I have seen really good people who know a lot of this maths, who know very high standard maths, and then when you ask them to implement the algorithm, maybe because they haven't implemented much of the things, and mostly it happens with academicians, people who work in academia, who work in research. They don't code actually. So it's not that they don't know how to code, they don't even think that coding is necessary. So here they have a lot of mathematical knowledge, but they are not able to implement it. But I see the other people, so who are from tier 2 tier 3 college, some people have given them tutorials and they have seen GitHub repository and copied them and followed tutorial line by line. Or then they have probably this, they have code, and the first thing they don't understand why code is doing it is why it is performing certain thing. Okay, and maybe they are good at some people have practiced so much, they are good at this, but they lack this. So but in order to land at a good job, in order to have a career in this, you must have both of the phases. You must have mathematical notion, and at the same time you also must know how to code these things and have real world applications. Is it clear? So what I'm saying is this PCA, so this is principal component analysis. Here we won't be going into the derivation of mathematics, so because this derivation includes calculus, so it includes calculus. But the concepts that we have learned so far, we'll see what PCA is according to that. So in PCA, so we have some data. Let's suppose we have some data matrix X, which represents something like this. So we have this X1 over here, X2 over here. These are data points. So this is our X matrix. So in order to project the data onto the lower dimension space, so whatever you have seen, so we have these projection matrices. So here the assumption that we have is that variance contains information. Variance contains information. Okay, this actually is a dimensionality reduction technique. So what is that? We'll see that into detail when we'll go into the PCA after learning the optimizations. So what I'm telling you now, right now, let's suppose you have a data point. This data point, let's suppose, have 100 columns. Okay, so now you have, let's suppose, 1 million data points, and each one has 100 columns, 100 features. So if you go on training a model on this, it will be really computationally heavy. So it will be computationally heavy, because there are 100 features and you have to train your model on 100 features. So for that, what we try to do, we try to only capture the important features. We try to capture important features. We try to see, can we reduce these 100 features, let's suppose, to some 10 features, but these 10 features should have the most prominent information that is there. Okay, maybe we have 100 features, but I want to get it down to the 10 features. That's why it's called dimensionality reduction. So dimension basically was 100, so now I'm reducing to 10. Okay, so this is the assumption. The assumption there we have is variance contains the information. So I'm saying that variance is the one that contains information. So if variance contains the information, I'll preserve variance. So again, this variance concept comes in. So I have actually taught you what the concept of variance. Just go back to that, and I will again delve into deeper data variance when we'll go going through the stats. Now here I want to show you the part of algebra while it's involved. Again, the PCA mainly is used for dimensional data reduction. So what is that? If you have a lot of features, you just want to reduce the features, but you must capture the most information that is there. So that's why you want to preserve most of the information. And now we say that variance contains the information. That's the assumption we have. Variance has information. Now we want to preserve variance. We want to preserve this because we assume that variance is the thing that contains information, and now we are trying to preserve this. And how to preserve the variance? So if you see that we make what is called as covariance matrix. Again, we'll go into this what is called as covariance matrix. That is some matrix. You know that so far there is something matrix of transformation. And this Sx, if you have this, for example, let's suppose this data point u1, and then we have this some lambda u1. Okay, our thing at hand is this. So this is like the general equation of PCA when you will bring it. You will preserve the variance, and what you will do, you will take the principal components. Principal components will be basically the eigenvectors. Eigenvectors will be the principal components. This will be our principal components. So this is the equation of PCA which you will see on the books. But I'll derive this equation, I will see, and this is what we call as covariance matrix and stuff like that. So here the point I want to give you is that we take these eigenvectors. That's why we say that we can preserve this information. We can preserve the maximum information by preserving the variance, and we'll choose these principal components, and we'll project our data on principal components. Project data on principal components. Let me give you an example like this. Let's suppose I have some three-dimensional data, so which is something like this. It has a lot of data is there, and I have some data. So what I want is I want to convert it into 2D, because 3D, let's suppose, is different, difficult to visualize. So I'll just capture two features. So let's suppose this is my first eigenvector and this is my second eigenvector. Okay. So now I'll capture this data. I'll project this data like this. I'll project this data onto this. This data will be like, projection will be like this, because now I try to find principal components. How to find principal components? So in order to find principal components, we'll find the eigenvectors of this covariance matrix. And covariance matrix, we'll find eigenvectors, and the eigenvectors which are corresponding to higher eigenvalues. So let's suppose there will be eigenvalues will be lambda 1, lambda 2, lambda 3, like this, and correspondingly we have eigenvector e1, e2, e3. Let's suppose this is sorted in this order. So that means this eigenvector 1 is more important. It captures more information. This captures a little bit less information than E1. This contains the least information. So I'll ignore this much. So I'll just take this lambda 1 and lambda 2 and E1 and E2. This will be my E1 and this will be my E2. I'll project my data onto this maybe high dimension data will project onto this 2 dimensions. Projection will be done on E1 and E2. Okay, we have done this dimension reduction, and it's also called as lossy compression. Why is it called lossy compression? Because you saw that we had 100 features and 100 was converted into 10 features. There was some loss, but there was a compression of data. Let's suppose you're compressing an image. Okay, you're compressing an image, and image has a lot of pixels, and if you capture the pixels in such a way so that you have the maximum information retained in that, and you convert and you did that 10 features, you have 10 most important features. So you said that I did a compression, but there was some loss of the information. It's not again that you will not lose information. You will lose information, but you are trying to sort of have the information that carries the maximum value. You are trying to capture that information, and that is captured by these principal components. So what are principal components? They're nothing but eigenvectors. Okay, and we'll get into details of this when we learn optimization, and we'll try to derive that mathematical that time. And now I just wanted to show you what are these principal components. Okay, and there is something called a lossless compression. How many of you know about Huffman coding? It's an algorithm in that data structure algorithm course. You might have seen the Huffman encodings. If you have heard about Huffman encoding, so that is a lossless compression. So that we do not actually lose information. We still compress the data, but it is not lossy. It is lossless compression. So this is the thing I wanted to talk about, this SVD and PCA. Okay, I'll stop this recording over here. I'll take matrix factorization.